to a presentation, and it is a great honor to have three speakers in this session. They are as follows: Professor Hans Go, and Professor Gabe Sibley, and Adam Ickenheiser. Let me introduce the first speaker of the presentation, Professor Hans Go. I introduced his biography. Dr. Hans Go is a professor of the ECE at Korea University. And Dr. Go received the BS degree from the Carnegie Mellon University in 1982, MS degree from the Johns Hopkins University in 1988, and PhD degree from the Catholic University of America in 1992, all in electrical engineering. And Dr. Go joined the faculty of the School of Electrical Engineering at Korea University in 1995. He served as the Dean of the Information and the Computer Technology at Korea University in 2004 to 2006. Since 2008, Dr. Go has been serving as the Director of the Samsung Techwin and KU Intelligent Signal Processing Center, sponsored by Samsung. Since 2010, Dr. Go has been serving as the Chair of the Korea University Robotics Research Group to engage in research on multimodal technology for HRI. Dr. Go has authored and co-authored over 500 papers in signal processing area and 36 patents in Korea and USA. His research interests include image and acoustic signal processing and enhancement for pattern recognition. Dr. Go has been nominated as the Director at Large of Region 10, Asia Pacific Region of IEEE Signal Processing Society 2010. Please welcome him.
Thank you for the great introduction. I was just a little bit afraid that the introduction was going to be longer than my presentation. But I hope all you had a nice and great lunch. We do a little bit, potentially might need a time for siesta, right? A little bit. But I'm going to try to make it as short as possible and give you an overview of some of the research activities that we have here on Korea University campus. So robotics research is it's a cross-disciplinary area. So we do have a lot of different faculties coming from different departments. I come from, as you can see, School of Electrical Engineering. So the way I like to give my briefing is to kind of give you a little bit of an overview and introduction on the research group at Korea University. And maybe the best way of doing so is to kind of walk through with a research course that we've just initiated not too long ago, which is called Human-Robot Interaction. So I'm going to kind of go through in this format. There are a lot of names here. I don't know if you can see from where you're sitting, but so the group here, the robotics group, as I said, comes from a number of different departments, particularly that of mechanical engineering. We also have faculties coming from the School of Electrical Engineering. We also, in fact, also do have a couple of faculties from psychology department, which, by the way, is a department over all the way in the liberal arts campus. We talked a little bit about some of the differences between liberal arts versus the science campus here, but we're very much happy to have some of the participation coming from liberal arts campus. But here, overall, the group has been devoted to a number of different areas. One, I want to call it as a scene analysis is one area, where we particularly look at the scene from the robot's point of view, where different things are located. What is the imminent things that's happening that the robot should be aware of? All these things are happening under the heading of scene analysis. We also have operator localization. This is when the robot particularly needs to be able to be aware who the person that this robot needs to listen to in terms of receiving commands. So in order to do that, robot needs to be able to identify who the robot's master is. So operator localization is very, very important. And third area is the task activity. And particularly, there are a lot of different things that robot could do in terms of reactions. But one of the things that also could be done by the robot being a moving platform all the time is that it needs to be able to give positioning by itself. So there's a self-localization and mapping is one particular area. A lot of faculties are involved. We also have, particularly those of the School of Electrical Engineering, involved with bidirectional interaction. This is when we want to have robot not just do passive type of activities. We want to be able to interact with human master. So bidirectional interaction is one component which becomes very, very important. Now, all these things, the four areas, they need to be combined together. And one of the elements, the techniques of being able to do that is by means of information fusion processor. We do that in terms of two levels. One is called middleware, and the second is to somehow be able to utilize the cloud computing. So a lot of the resources are not going to be localized or at a local platform, but will be at some server at some remote location. So we do need to kind of connect between two platforms, that of the cloud computing where all the information resources are, as well as that of the moving platform. So these four components make up the ones that kind of combines all these four things would be called information fusion processor. So I kind of listed out the names. I'm not sure if I've left out any of the names. If I do, then please excuse me. And I'm certainly very much open to more names there. Now, I want to kind of go a little bit about what are the challenges that we are dealing in terms of technologies. Here, being a robot needs to be interfaced with not just the world itself, but also a human operator as well. So it has both ends of being able to communicate. I've kind of listed out all these important components. For example, the robot movements, the action, navigation, and all these things having to do with how the robot sees surrounding the world, but at the same time, how the robot communicates with that of the human. For example, in terms of the gesture recognition, the speech recognition, all these are very, very important elements. So once again, merging and combining all these information would be that of, in terms of the middleware, and underneath that is the information fusion processor. So the idea here is that years ago, or until very recently, most of the robots that we are familiar with are very much humanoid. They're just movement oriented. And I want to say maybe up until very recently, even though it is very much intelligent robot, still being very, very passive. Now, what we need to inject nowadays is to make it more interactive. Interactive with human, interactive with the surrounding scenes, interactive with perhaps, again, by utilizing some of the resources from the cloud. So that's what we have, and here's an example of what we envision.
Greeting, it is a fine day. Mr. James
How a
Clark.
robot should perform.
Are there already people in the conference room?
So the robot kind of moves around. It looks at different people, performs recognition and verification, and also reacts to what the human says. Here, in this case, human gave robot a command.
There is no one in the conference room.
So there's a face recognition, tracking, and so forth. Another scene
Greetings.
where
Is it your first time to ISPL?
person
May
is
I help you,
identified,
sir?
My name is John.
asking for what the intention is.
Welcome to ISPL, Dr. Sean. Please have a seat in the conference room, and I will let Professor Ko know that you are here.
So a glimpse of a lot of the interactions taking place. And as you can see, it's not,
Yes, sir.
it looks very fun and easy, right? But if you can imagine that we developers, people who are developing robot, being able to perform very interactive procedures like that, it's just a humongous challenge. And it does indeed give us a lot of motivation but a lot of challenges as well. Let's look at a couple of different components here. Again, at the scene analysis here, and why we think that it's so difficult challenge. So here's a robot, and try to kind of figure out what is going on in the surrounding scene. And there are a lot of people either standing or moving, and that's, if they're just sitting and we can go focus onto the person, maybe face, and be able to recognize that will be okay, they might not be as challenging. But if the platform moves around, as well as the people are also continually moving around, that becomes very, very challenging. So we have to perform not just face recognition at one spot, but it has to be done over time. So it's a very sequential thing. You have to look at the history, how also the surrounding and the environment changes in terms of maybe sound, in terms of the lighting condition. If it's just too dark, okay, all of the sensories that the robot has may not work as well. The challenge is how do we overcome such environmentally challenging situation? How do we overcome, make it very, very environmentally robust? So that's one issue. Let's look at what the current technology is at this point. So this person, one of my students, is making comment, and as you can see, it recognized the direction of the sound of source, and then it also recognizes the gesture scene, which some of the faculty visiting today or this morning was able to see a couple of scenes like that demonstration this morning. And the system recognition. He's asking, when did I take my medicine? Obviously, the robot is providing some nursing assistance. So the robot responds that you need to take the medicine at 1 p.m. today and so forth. So as you can see, it's not just engaging in a conversation, but engaging in a conversation has to be done real time, right? And a lot of computing power there is probably very much overloaded. So computationally overloading, how do you reduce and make everything work real time, and being able to kind of feel that human interacting with robot makes it very, very, very natural, make it very, very, very real-time procedure. That's going to be pretty much challenging. Let's look at another scene here. This is a robot here. There are a couple of things going on here. Some sort of broken glass breaking scene taking place. But there are also, by the way, other sensors. We want to call it a perception sensor network that allows, with some sort of communication network, sending information to a moving platform, which is the robot. So if there are, cameras and microphones sending information with certain accident taking place, here, as you can see, robot may not be aware being at this location, rather remotely located away from where this incident occurs. Indeed, there are other sensors that are also going to be able to help. Only thing that they can do that is when they're connected. So connection, the networking becomes very, very significant challenge at this point. So these are, I kind of itemized, different technologies there, important components from 1 to 5, 1 being the scene analysis, the operator localization, bidirectional interaction, task activities, and there will be information fusion processor. I'm going to kind of go very quick. I'm kind of running out of my time. Here's an example of a scene analysis. It needs to look around the scene, the background, and also be able to recognize where things are and what these things are, right? So there's a need for classification using shape and visual features. There could be also certain things moving objects. For example, if the robot is standing here, there might be some sort of a moving object, another maybe robot. imminent collision on course. What do we do? Right? You gotta kind of process that information and be able to make certain actions there. So motion modeling also becomes very, very important. I kind of listed out some of the technical issues. I want you to kind of take a look at the brochure and go through these issues. I want to kind of identify maybe one that kind of pops up here. This is a localization and tracking, another big issue with maybe sensors, with maybe different lighting, how the structures are surrounded. There's also need for path optimization. A lot of work has been done on this area here. But still, I mean, there are plenty of objects that are not necessarily in some very, neatly arranged fashion. So there's a definite need of a lot of different sensor, data fusion of network imaging sensors there as well. We could also perform sound recognition. We kind of saw that a little bit through the another slide there, so I'm going to pass that. Speaker verification is another hot area, being able to recognize who the master is, and perhaps use that also be able to segment, different persons. Operator localization is, as we kind of gave you a demonstration this morning about where the sources, which direction the sources came from. That also becomes very, very useful information. Human detection and tracking. Here, so if there are a number of people kind of sitting or doing certain activities together, right? If I were the robot, how do you recognize that that person, say, standing in the middle is indeed the person that I'm trying to communicate with? That's going to become very, very challenging because all these three people are kind of, overlapping each other. There's a lot of, people that are not necessarily all separated. So separation becomes a big challenging issue, and we have to do that in terms of, all kinds of different lighting conditions. Bidirectional interaction. There are two different types of ways that we could do is maybe by using gesture and with speech. So other maybe ways that we could do is maybe some sort of tactile sensors is another area that I think one of the faculties in the mechanical engineering department does that research a lot. So some sort of schemes for performing interaction becomes important. Just kind of pass through the information fusion process and said that this is what we need to be able to merge all the different components. Let me go through the fusion processor here, why this becomes important. So, so a robot performs some of the scene analysis, knows where the operator is located, and it does it by means of a series of Q&As, right? Asking questions using some sort of bidirectional interaction. So out of that, there are certain decisions that needs to be made. And the question here is, with the decisions, okay, that would be made through middleware and information fusion processor. But here, then the robot needs to do certain reactions as a result of that. And the way it will do is by making certain reordering the prior list. Suppose, for example, robot receives certain order by robot's master. Let's say go to room 321 and bring certain patient's chart. But while en route to that room, this robot finds some person, right, kind of collapsing. Okay, then the prior list needs to be reorganized or reordered. And so that's the kind of thinking process that robot needs to go through. So therefore, a lot of these models also, models of actions and models of decision procedure, models of the priority needs to be developed. Cloud system also becomes very important because that's one of allowing resources, like as you might have known, using Siri, right? You could engage in conversation using your smartphone. But that doesn't mean that all the recognition and a dialogue system is embedded on the smartphone. It's actually serving that capability from a very remote server. And that's what this cloud system is all about. If you want to have different models for different actions and reactions by the robot, then we need to have plenty of memory space, and that can be done only with a cloud system. The other thing is that what if there's a robot here, then there's another robot which is kind of closer to where things of more important significance happening at the same time. Then we need to have certain hands-off type of steps taking place. So that could be done only when you have this cloud computing where all these information that are gathered are again computed in one common area, and we call that again as a cloud system. That's where the information fusion processor is located. So all these 6 components are the ones, different technologies and techniques where most of the factors involved with the robotics area now at Korea University are engaged in. There's still a lot of work that needs to be done. We're very much excited. We're looking at a number of different scenarios of application. This is for the robot that's kind of roaming around outdoor. An outdoor activity and surrounding environment is also another big challenge. I mean, for example, like that's when Kinect, for example, would not work outside. So gesture type of algorithms that could be used indoor cannot be equally applicable outside. So we will be looking into, there's even more challenge for outdoor activities there as well. We also look at a lot of application scenarios for indoor services, particularly that of the nursing assistance type of services. We do have a hospital here on Korea University campus. That's the same way at GW. So here in where the patients are located, a lot of assistance could be provided by localized robot. For example, this patient is obviously going through some sort of pain, needs some sort of help by the robot. I didn't have the time to finish all the translation there, so certain things are still in Korean. But essentially what it's trying to do is that robot provides services there. So it's one of the scenarios that we're looking seriously. And of course, we also do have other scenarios that we're also looking. One is in the teaching, where teaching assisted robot. A lot of efforts or desire by the parents of students wanting to learn English, for example. Okay, so very nearby, an assisted robot could provide that kind of training very effectively and efficiently. But then at the same time, what are some of the important technologies that are involved? Tour guide and nursing robot, we do have a lot of tourism is very, very active in Seoul. A lot of shopping going on, and also home care. The age, the population of the Koreans nowadays is growing old, so we have to kind of start preparing for that. So this is another area that we're looking for potential application areas. I understand that some of the faculty from GW are working on airborne type of vehicles. Just want to say that there are a lot of high-rise buildings in Seoul, and if these high-rise buildings catch fire, you were just in a very bad situation. As a matter of fact, there was a movie that just came out about a month ago, had that scenes of trying to handle this fire situation. But high rises as far as high as like 50 stories high, not very much reachable by the ladders alone. So it has to be done by some sort of airborne approach. We believe that maybe that might be a great area that we could jointly work together. Okay, well, just also want to say that we do have plenty of a great facility. As you've seen, amazed by this Hana Square, we do have a lot of other research facilities to accommodate. There are big and airborne type of robots that could be made available to us. We can accommodate them. Okay, so I want to kind of thank you for your time. I think that's my 20 minutes.
Thank you, Professor Go. Okay. First, the Professor Gabe Sibley. I'll introduce his biography. Dr. Gabe Sibley is an assistant professor in CS at the George-Washington University and the director of the Autonomous Robotics and the Perception Group. Professor Sibley received the BS degree from the Emory University in 2001 and PhD degree from the USC in 2007, all in the computer science. And Professor Sibley was a robotics engineer in the computer vision group at NASA JPL under Dr. Larry Mattis. And NASA JPL, Professor Sibley worked on long-range data fusion algorithm for planetary landing vehicles, unmanned sea vehicles, and unmanned ground vehicles. His interest is in the probabilistic perception algorithm and estimation theory that enable long-term autonomous operation of the mobile systems. Please give him a warm hand.
Thank you very much. I think the siesta is in order. Lunch was wonderful. And now, of course, a little bit of a food coma. So I'm going to talk about AI and robotics at GW. I'll introduce a number of my colleagues throughout my slides. I'll dwell on my own work a bit more of necessity. And then I'm going to hand off about halfway through to Professor Adam Wickenheiser, who will talk about a bunch of the other work taking place in mechanical engineering. So why AI and why robotics? Here are 9 applications, and these are present-day real-world examples. We're exploring Mars right now with our second, third generation of very successful rovers. And obviously, we can't do this yet, so we need autonomous machines to help us with the job. This is same story for accessing hostile environments like exploring under API sheets. Right? We're not going to go there, at least not for very long, and do any sort of interesting science. Autonomous aerial vehicles are, of course, useful for surveillance and other applications. Autonomous cars. This is going to transform society. This is one of my pet favorites. Rio Tinto has invested literally billions of dollars in automating mines in Australia. Kiva Systems here was recently acquired by Amazon to automate a large percentage of their operations in their warehouses. So these machines are really coming online now. Bottom right here is an example that we're actively involved with. There may be a room for collaboration with KU. Perception in the pocket, the algorithms that we're endowing robots with are really going to run on our cell phones, and these are going to be intimately related with algorithms that are running in the cloud. Right? So these are clever little devices, and they're only going to get more clever. There's only ever going to be more of these sensors on our bodies and in the world. So it's fun to watch that transition take place, and it's happening very rapidly. So my own work is really focused on perception, teaching the machines how to see. So on the top left, you see a 3D colored point cloud being created as a robot. This robot here, Lisa, is driving around a quad in New College in London, in Oxford. And on the top right, you see the quad after it's been created. So obviously, these are just points in 3D space, and it makes our brains excited, but it means nothing to the machine. You've got to do more work if you actually want to transfer knowledge to the machine. So perception comes before action. If these machines are going to be ubiquitous, if they're going to be in use everywhere, then we have hard problems to solve in perception. Before a machine can act intelligently, can behave intelligently, it needs to acquire models over which to plan and act intelligently. So control requires sufficient statistics that describe the state of the world. Scalable knowledge representations, and scalability is very important if you want long-term economy, systems that operate indefinitely without human intervention. We require constant time algorithms. They must be fast. The robot can't slow down the weight of its own computations as time goes on. need to function in novel environments. The world is not a static place. It's forever changing. So you have to be flexible and plastic. Whatever estimation theory takes place needs to take that into account. And really, we require embodied systems. As roboticists, we fundamentally believe that. You're not going to ever know if the system works if you haven't actually applied your theory to the experimental apparatus, which is the robot platform. So perception is the hard problem, whether you're building 3D point clouds of the Mars yard or indeed on Mars, whether you're trying to avoid boats as a robot traversing autonomously through a harbor. So this is long-range perception here. This is an autonomous boat for the Navy. Or you're a highly dynamic platform like the Big Dog robot. So developing perception systems for Big Dog that can work through these crazy motions that the vehicle is capable of is very challenging. So pushing the envelope of perception is a challenging task. So what are we talking about here? Well, we're talking about what the business people call simultaneous localization and mapping. And it's really the inverse of what's done in computer graphics. So a movie like Shrek here will take a mathematical model, a parametric representation of the world, and transform that into a sequence of images that we watch. We do the exact opposite. We take a sequence of images and try to infer the mathematical model that must be there to explain what you see. We do that in over, say, 50,000 stereo frames. We produce models like this over a few kilometers. So this is an example of the type of model we're trying to infer so that we can then go on to make intelligent choices. So we're really interested in temporally and spatially scalable solutions to this problem, the so-called where problem. How to know where you are and where objects of interest are if you're an autonomous machine. So for example, here is this robot Lisa going around and collecting data. It's got a stereo camera pair up front, lasers on the side, an omnidirectional camera on top. And this down here is the left and the right image, and features being matched in the left and right image and tracked in time, all of which allows you to uncover the geometry, the trajectory that the vehicle has followed. And this is endowing the machine with basic spatial awareness, right? So this will go on and go for a number of laps, and this is the open loop system running here. And it runs for 2 or 3 kilometers, at which point it's only made a mistake. It's only drifted by 2 meters, so it's not drift-free because it's just vision-based, but it's still quite accurate. And you can see this is the overlaid solution on the actual college. But we said we're interested in spatially and temporally scalable systems. So actually here you see this is that trajectory, that 2-kilometer trajectory that was being estimated, and that's embedded in a much larger map here around Oxford. And then here's Oxford, and here's the trajectory going down to London. And here's a bit more of this trajectory along London. So this is 121 kilometers of purely vision-based estimation. So trying to, again, endow the machine with an understanding of its spatial relationship to the environment. This is carefully anonymized for peer review. This is the system that was actually used for data collection. The stereo pair on top of a bicycle helmet and a laptop on the back. And as I said, these are being replaced with cell phones now. So it's over 7 hours, 121 kilometers, 200 gigabytes, many complicated real-world scenes like riding on a bus or an escalator or an elevator, riding the boats on Ferris wheels, things like that. Okay, here's a bit of the beginning of this data sequence, and you can see here the red, green, and blue X, Y, and Z position of the vehicle or the user as this system evolves in time and the features being tracked. And the point here is that this is not carefully collected data to make the problem easy to solve. It's explicitly from the wild, difficult situations, as you would encounter if you were a natural humanoid traversing natural human spaces. You can see the user here is looking down, getting ready to get on the bike, and you can see the direction that the user is looking by looking at that red vector. And as he rides away, you'll see the constant velocity motion estimate of the bicycle. And this is the type of challenging situation that we're going to encounter in the real world, right? We want to open up that performance envelope to challenging lighting conditions, extreme motion blur, dropped frames. If somebody covers one of your robot's eyes, it still needs to function, right? So that type of robustness is actually extremely difficult to obtain. That's where a lot of the future work still remains to be done. And just an example of what you can do with this. So you have here, same system working on a vehicle. This is the beginning of a 1,000-kilometer sequence that's testing place recognition and object recognition, loop closure algorithms. And what you can see is the actual geometry of the road starting to unfold. We see it obviously. So armed with that, you can then try to generate synthetic overhead views and actually match what you see on the road to what you would see from an aerial image or from a satellite. So this is GPS level pose estimation without satellites, and just by matching what you see on the road to what you would see from overhead, right? GPS without satellites. And of course, this is going to be really important for automating the highways. I always like to tell the story, 10, 15 years from now, maybe sooner, our kids are going to say, wait, you used to get in those metal cars and turn wheels and pull levers and step on pedals to make it go? You guys are crazy. You should let the computer do that. It'll be way safer. And they'll be absolutely right. And it's going to revolutionize our relationship to the vehicle and to our cities. It's going to be like a transformation from before automobiles to having automobiles. So that's a big impact that our science can have. The future is also fast, so pushing that envelope on perception on platforms like Big Dog or Rex or this quad rotor here, which is cheating because it has off-board sensing, is very challenging. And we believe that the future there, this is work by a postdoc, is in dense systems. So estimating where every pixel is. This is many gigabytes of data per second that's being processed. Too much to send to the cloud, but enough to really understand the local metric 3D structure that you're interacting with. And that gives the system quite a bit of robustness. And of course, armed with really nice dense 3D models, then perhaps you can do interesting things. So this is ongoing work where we're trying to really tie the loop between dense perception, build these models, and then plan, paying attention to the physics, the underlying interactions with the real world, so that we can hopefully do things that you can't do otherwise. See, it's not quite there yet. The goal here is to build a car-catching robot, of course. Okay, so the Positronics Laboratory, partner in crime here, Professor Evan Drumright. He is an expert in robots and fast dynamic simulation. So given these models from perception, Evan can tell you how the contact forces and the restitution forces and how you should go about simulating your interaction with the environment to get accurate results. These are his students here in the Positronics lab. And that's not our PR2, but we actually do have a PR2, which is a wonderful platform for testing these situations and these experiments. Of course, there was great reference to natural language processing and actually speaking to these machines. And that's what we want to do, right? We want C3PO, who is familiar with over 6 million forms of communication, so that we don't have to type, because we're really bad at communicating by typing, but we're really good at it by just speaking. So that's where you get into natural language processing. And we're fortunate to have Mona Diab, so if you're interested in NLP, she's recently joined GW, and she is a world leader in NLP, and specifically in text translation and Arabic language, statistical approaches to NLP. And of course, NLP is intimately related to machine learning, computational statistics, and NLP obviously fits within the taxonomy of subjects within computer science, and it's a very core technique. A lot of the techniques that we actually use in computer vision are borrowed from NLP. Who uses NLP? Well, today, obviously, Google. We're talking hundreds to $1 billion, $100 million to $1 billion. And this is another technology that we're intimately involved with that is going to transform society, especially coupled with solutions to the perception problem along the lines of object recognition, place recognition, and relating that to the symbols that live underneath. Machine learning is intimately related again with natural language processing. So Claire Monteleone has recently joined GW, and she is actively working in machine learning. Her interests are particularly to do with climate modeling and climate informatics. So that's applying modern techniques from machine learning to advanced climate models. And she's had quite a bit of success running a workshop on climate informatics, which is getting a lot of attention. So these are modern computational statistics, modern techniques applied to very pertinent problems in sustainability and climate modeling. Okay, so with that, I'm going to hand off to Professor Wickenheiser, and I'll tell you about a number of other ongoing projects at UW.
Thank you, Sibri. And we have the second part of the presentation by Adam Wickenheiser. Okay, I introduce the biography. Dr. Adam Wickenheiser is an assistant professor in the Department of Mechanical and Aerospace Engineering at the GW. He received a PhD degree in aerospace engineering in 2008 from Cornell University. In January 2010, he joined the faculty at the GW. From 2008 to 2009, he served as the postdoctoral associate and the visiting lecturer at the Cornell. He is the secretary and the founding member of the ASME Technical Committee on Energy Harvesting. He was awarded an Intelligent Community Young Investigator Award in 2011. His research interests are in the area of the bio-inspired aircraft and the control architectures, adaptive structures, smart materials, and fully structured interactions, and energy harvesting. Thank you.
Thank you very much for the introduction. And thank you very much for the opportunity to speak with you today. I'm going to focus my part of the presentation on some of the efforts of our Center for Biomimetics and Bio-Inspired Engineering, also known as COBRA. The director of this center is Dr. Mike Blesniak, who is also the chair of our MAE department. And the goal of this center is to take a look at engineering from the viewpoint of nature. So nature has had millions of years to evolve. So there's been a lot of trial and error, natural selection. And they do some things extremely well, particularly looking at multifunctional materials. So you have limited resources in nature. So you try to make the most of what you have. And that means that you need to be able to do many things with a small set of actuators, sensors, and integrated into your structure. So we're looking at, as its description says, more energy efficient, agile, adaptable, fault tolerant. Of course, if we start to break down, then we need to be able to either regenerate ourselves or find a means of regenerating ourselves. And environmentally friendly, and also multifunctional, as I mentioned. And the thing that I find interesting about biomedics is that it's at the crossroads of a lot of different disciplines. So these are the major categories within our center. I'll be speaking about the first and last one here, aerodynamics, as well as biomimetic robotics and autonomous systems. But none of these things are possible without advances in materials, as well as the computational side of things and the control side of things. And we also have a few applications for biomedical engineering tools. And so these are some of the faculty that are involved in COBRA. And some of these, of course, are in our department, and ECE, CS, and then also outside the School of Engineering. So we have biologists as well involved in the center. The first project that I want to talk about is looking at multi-scale continuum robotics. So there are many examples of what's known as these biostats. So they're deformable parts of the body or the entire body. And the thing that's interesting about them is that not only can they form a very wide variety of shapes, so they have a large number of degrees of freedom, but they also have continuous distributed sensing along the length of their body. And many of the applications include being able to penetrate areas, very small areas, and be able to be self-aware of their surroundings and be able to morph their shape in order to fit into areas that maybe a larger robot or a statically configured robot might not be able to. So of course, the one thing that jumps out is doing surgery or detecting, if you need to do some type of invasive either sensing or therapy inside the body. You want to make the incision as small as possible, but you also might not know ahead of time exactly what route you need to take to get to the area that you need to either do your sensing or do your surgery in. So the the coupling, the multifunctionality needs to exist between the actuator, the distributed actuation, and the distributed sensing. Because of the fact that you don't know, not only is it difficult to form all these different shapes, to be able to coordinate all the different actuators to work together, but you may not even know what shape that you want to form. So when you start to go into the body, there's got to be some way that you can work with the surgeon, but also do some use local feedback. So if you start to run into something, you need to be able to decide, do I want to go through that, or do I want to go around? So that sensing has to exist there as well. And of course, this is something that is very easy and sort of second nature to all of these animals that can do these things. So they use sensing along their whole body to be able to manipulate objects, to be able to locomote, and sort of transition between the two as needed. So of course, on the right there, the monkey there uses its tail both for grasping and manipulation, but also for locomotion. And some of these other things, they use those as well. We can scale this up to a larger size, and this is a picture of a larger robot sponsored by DARPA, which uses similar ideas in that it can reconfigure itself, so it can go from a purely translational motion to be able to unfold, to climb upstairs, to be able to go over obstacles, to be able to span gaps here, actually go from horizontal to vertical and then horizontal again. And it's also multifunctional in that the same linkages that are used to do all of these geometric changes can also be used to manipulate the environment. So you think again back to the monkey's tail can also grasp things and carry things, as well as being used to aid in locomotion across large gaps and through trees very quickly. So we have, again, we have this sort of adaptivity between the locomotion and also the manipulation. So again, we have the same components here operating the door handle as would be used for manipulation and also for dragging it along if it was needed. And the thing that's interesting about this is his words, this is Professor Ben Sweet's words, that it has a high payload capacity, so it can actually carry himself as it goes through these different morphological changes. So this is a little bit of my research here, another bio-inspired design. In this case, we're looking at wing design and incorporating some of the features of bird feathers. So one thing that's sometimes a misconception about bio-inspired engineering is that we're trying to duplicate what happens in nature, and that's not the case here. We're still using man-made materials, and we're trying to approach natural systems, but also keep in mind the fact that we can do some things that nature can't do. We have these revolute joints. We can put processing into the actual sensors and actuators to sort of short-circuit the feedback loop. And one of the things that I'm interested here is looking at very small and very lightweight vehicles. So there's a large demand for bringing unmanned aircraft, into smaller, tighter environments and also unknown environments where you might need to make split decisions. As you shrink the size of the aircraft down, you necessarily have to shrink the weight of the aircraft if you want to fly it at low speeds, low enough to avoid collision in these tight environments. And unfortunately, that's sort of a deadly combination when it comes to wind gusts and turbulence, because now you're talking about a disturbance that's significant compared to the total energy of the system, or the total inertia of the system. Not only that, but you have this very structured turbulence around buildings here. And this is a simulation, I believe it was at MIT, to look at the flow around different man-made objects. And you can find similar simulations through forest canopies and across mountains. So you have these large form structured gusts and wind disturbances that are on the same order of magnitude as the size of the aircraft. So one wing could be experiencing a completely different flow from the other wing. One wing might have an attached, very almost laminar flow, while the other one could be completely turbulent, or could be experiencing a vortex shedding oscillation that interferes with one of the dynamic modes of the vehicle. So there's a lot of unknowns that occur here. But of course, birds can fly through these environments very easily, right? So you can see, particularly, one thing that comes to mind is looking at seagulls on the shore. You have these very strong winds coming off the water, and yet they're able to make these very small adjustments with their wings, particularly the wingtip feathers, and remain almost hovering in the face of these very strong winds. And they can keep their eyes steady. So scavengers, birds of prey, obviously to feed, they need to be able to detect. They need to be able to detect the prey that they're going after. And if they're being constantly rattled by turbulence, they're not going to be able to see these things from great distances. So of course this has application in surveillance and also targeting and mapping, where you might be very with the sensitivity of the sensor, whatever that happens to be. You might need to be able to remove some of these disturbance loads that you get from the turbulence. So we're looking at how we can sort of mitigate that and isolate it towards the wings. It's almost like thinking of a reflexive action. If you touch something hot, you're going to remove your hand before your brain even registers that you do it. So what we're looking into is how do we put some of this intelligence of how to respond to wind gusts into the wing itself, so that we're locally responding to the disturbance and not relying on inertial measurements, so not relying on a change in acceleration or rotation. It's sort of thinking of that way is kind of considering the disturbance to occur and to have an effect that's detrimental, and then waiting for that detrimental effect to occur before you actually respond to it. So we're looking at how we can remove that part of the feedback loop from the autopilot, from the central processing, kind of from the brain of the vehicle. And so this is the design that we came up with here with these segmented panels. Oops, excuse me. And this animation here just shows some of the different configurations that the panel has. And what we're really looking into is actually propagating the response to this disturbance and keeping it local to where it occurs. So for example, if a wind gust happens to hit the center of the wing, then you would respond to it right where you detect that wind disturbance. So those sensors that detect the change in pressure would then have a counteractive response. And if those feathers can't generate the necessary counteraction to keep the base, keep the fuselage of the vehicle stable, then they would propagate that error signal to its neighbors, and then they would start to chime in and they would start to respond to the error. And if they can't respond, they would move to their neighbors, so on and so forth. So it keeps the response as local as possible, and it keeps it scaling up so that you don't involve sort of too many actuators or too few actuators, depending on what the disturbance is. Another thing that's interesting about biomimetic engineering, when you start to actually look into how these systems respond in nature, is that there's always a mix of a passive and an active response. So if you look at traditional robots that are rigid structures connected with a finite number of actuators, that's basically a fully active response. Everything that occurs is occurring because you tell it to, or the intelligent feedback tells it to. But if you want to really respond to the unknown, you need to have some passivity built into it, in order to increase bandwidth and to localize the response to the disturbance. And so what we're doing is we're going to develop these electromechanical feathers. So this isn't to scale, by the way, this represents the feather, and then we have this system down here in which we use a voice coil both to direct the angle of the feather, but we can also do a switch between a fully active and a fully passive mode. So we can actually use the voice coil not only in an active sense to direct the motion, but we can also use it to change the stiffness and the damping of the system dynamically during the motion. And of course, we can also use the system to detect the force and the displacement. And then again, this switch here, which is just representing a transistor, can be used to toggle between either fully active or fully passive response, or by just using a variation duty cycle, a combination of active and passive. So we can explore that whole space, that whole continuum between a fully passive fluid structure deformation and an active one. So this is the wind tunnel test facility that a number of the faculty members in COBRA, our biomimetic group, use. This is located at our Virginia campus in Ashburn, Virginia. The thing that's interesting about this wind tunnel is that we have a programmable turbulence generator. So basically, what this is it's a series of panels that are able to either rotate so that they're completely blocking the flow, or they can move so that they're parallel with the flow and allow it to pass through. And this can be programmed by our data acquisition system. So right now it's being used for two different experiments. One of them is to simulate vocal folds and the airway that passes through the larynx, and that's Dr. Plesiak's group. And we're also using this to be able to reproduce the type of realistic flows that you would see if you're flying down the street between buildings. And you have the mean flow, and then you might have a cross flow coming from an alley or a cross street. So we're able to actually simulate some of those large structured disturbances in the wind tunnel. And so we have our test section here with a wing section, and we can actually remove panels along this section and install our series of electromechanical feather modules, and then measure the overall aerodynamic forces of the load cell down here. This is another project by Professor Megan Leftwich, where we're looking at bio-inspired swimming robots. And in her case, she's interested in the propulsive mechanism of how vortices are shed from the trailing edge of these very elastic, very flexible fish. So the actual animal that she's interested in mimicking is a lamprey. It's a fairly old animal. It's been around much longer than most of the other fish that we have present day in the ocean. But it's also a very capable swimmer. And it turns out that there's a very strong coupling between, again, this idea of being somewhere between fully active and fully passive. So of course the fish sends commands to move its tail back and forth, but there's also a fluid structure coupling between the passive flexibility of the tail and its ability to shed vortices in order to propel it forward. And so what she has done is she's created this robot here with 13 segments, and the path planning that this robot takes is actually based off a video of actual lampreys. So based on the speed that the robot can attain, it changes its shape in order to match the curvature of an actual lamprey swimming at the same speed. So this is the robot, without its skin, and then once its skin is put on, it's able to be fully immersed in water here. And so this is just a little video of the actual robot here swimming. So this, the form that it takes here is, at this particular speed, is actually the exact same shape that is recorded from an actual lamprey. So she matched both the active deformation of all of these servo motors to the active bending in the actual lamprey, and also matched the skin that's over it to the actual stiffness of a lamprey skin. So both the passive and active deformability are matched in this case between the man-made system and the natural system. And another project, which unfortunately wasn't able to get a video of, is looking at cetacean swimming, so dolphins and whale, particularly their tail. Again, how they use both active and passive deformation in the swinging of their tail back and forth. And this mechanism here actually rides on two rails, so these are a pair of wheels here. So the rails go along the side of a long water channel, and it can be either self-propelled or it can be placed in place and then allowing the water to flow through. So they're looking at combinations of both the static and the dynamic swimming. And this thing looks pretty complicated, and the reason is because with this mechanism they can actually affect the phasing of the thrust of the tail and also the camber. So how does the tail move back and forth, and can we mimic sort of the passive and active deformation by scaling how the camber is coupled to the thrust motion up and down. This is another project that I'm working on actually with the Naval Research Lab. And as part of COBRA, as part of our bio-inspired engineering program, we're also looking into bio-inspired control systems. And in this case, we're looking at how groups of unmanned aerial vehicles can move over the water and maintain a formation that minimizes some type of cost function that may be minimized in order to maintain a certain level of communication, maybe minimized in order to maintain a certain coverage if they're looking at the sea, if they're trying to find submarines, something like that. But it becomes very tricky because, of course, over the open water you have very strong wind gusts, and again, they're very structured. So you don't have sort of a random white noise gust, you have something that's correlated, particularly when you're only a few wingspans above the water itself. So once we got down there, we found that we could actually generate some coherent models of the wind-water interaction. And so sort of phase one of our study was to develop these models and put them into a form that we could actually do some control design. So put them into the form of a stochastic structured disturbance into the wind. And the other thing that we needed to do is that a lot of the quadrotor models out there assume basically a thrust is proportional to the speed of the motor relationship. And because we wanted to incorporate the effects of these structured gusts, we actually had to go back to the model here and break it down into this, what we call a blade element model. So we need to take into account the suction, the downdraft, due to the spinning of the propeller and also due to the wind model here that's coming through. So this is a simulation of just one of the vehicles flying through this wind model. In this case, the wind is going top to bottom, and the vehicle is trying to fly left to right here. And basically, it takes a little while for the vehicle to realize what's going on. But as it goes, as time evolves, it actually takes into account the pattern of wind that's coming over here. So in this case, it's a little bit of a simplified model because we just have a constant sine wave of the surface of the water. And so the wind that's generated over there is obviously going to be correlated, and it's something that the vehicle can learn as it starts to fly over time here. So this is just one vehicle, and what we're interested in looking at is what if we have a group of these vehicles, and you have this very correlated structured gust passing through the group. So clearly it's going to affect the vehicles in the order in which they're placed. So if the gust is coming in from the north, then the northernmost vehicle is going to feel it first. So it should be able to communicate that information to the vehicles down to the south so that those vehicles can then reconfigure themselves before the gust hits, so that once the gust hits those vehicles, they'll be sort of pushed back into the configuration that they need to be. So we're looking into developing sort of a neural network, if you will, between these different vehicles, and the information that they're going to pass is the gusts that they see coming in from the wind-water wake interaction here. Okay, so I think I'm about out of time. Yeah, so I think I'll just end right here. All right, thank you very much.
Welcome to the third session, which is nanotechnology session. I am working from the Department of Material Science and Engineering. Our first speaker for this session is Professor Volkan Zogar. He earned his PhD from University of Berkeley, and then he recently joined George-Washington University. He has been working on investigating novel optoelectronics devices and energy conversion solutions, primarily at nanoscale dimension. He's been published many good papers, such as Nature Science and Nature series of papers and things like that. So very excited about that. Let's welcome Professor Zogar.
All right, thank you very much for this kind introduction, and it's been a pleasure being here and learning about your research and sharing this experience. I'm showing you today research about nanotechnology at GW, and nanotechnology is very interesting because it can potentially fundamentally change all the devices that we build, systems that we build from the bottom up, really from the ground up. And with nanotechnology, for instance, like there are three key items that in particular also my group is interested in, and we're interested at GW, that's nanophotonics. Nanophotonics, for instance, I demonstrated you can make world's smallest lasers, and lasers are very important devices for telecommunication and for various applications. Secondly, for instance, we are looking into optoelectronics, and we can actually we can make optical transistors, so future computing can run with light. That's something that my group is very interested in as well. And one other part that is very interesting is we can use these nano devices and materials that we learn at this scale to implement this into very efficient solutions for instance, like here for record high solar efficiencies. In fact, from this simulation point of view, we are able to get past to 50, that's 50% of efficiencies for solar cells. So very exciting things. Ladies and gentlemen, this is Nito. Nito is a cleaning robot that cleans the apartment of my wife and myself, which is very nice. And if you basically plot that computing power of this machine, which of course is the utility robot, here on the y-axis, basically million instructions per second over time, it's somewhere about here, and it kind of corresponds to the brain power of a lizard. And the idea would be, well, the lizard is great. Can we go to a mouse, maybe a monkey, or can we even, simulate a human brain? So the idea would be for these kind of systems, these robots, of course, to go basically up this curve. And they need a lot of computing for this. And basically, as we heard before, we need a lot of computing performance power and data signaling power in order to use these functions. However, there's a challenge, and post there's one global challenge on that, and it essentially is always given by that slope, or by this kind of graph. This is Moore's law, as you know from Intel, for instance. So here I'm showing the gate length in micrometer, for instance here, in micrometer versus time, and we were kind of been scaling down. And of course, this is what Samsung is doing, Intel is doing, IBM is doing. That's great. That's perfect. That's why we have smartphones, which were like supercomputers 10 or 15 years ago. Now, but you see down here, we're getting to really, really small scales. Can you just split atoms at the end? I mean, that would be a big challenge. In other words, currently, like these transistors in this, probably like this computer running this PowerPoint in this very second, has a gate length of about like 35 nanometer, probably, like basically on this order. And if you zoom in here, we basically have this kind of gate length, or this kind of gate oxide here. And you see actually these little dots, do you know what these dots are? They're individual atoms of this material. And that's getting to the order of like 10 to 12 atoms in an ultra-scale device. That's not much. We cannot go much beyond that. In other words, we are down to the individual atom level very soon. And by 2020, essentially, the International Technology Roadmap Semiconductor says scaling is done. No more scaling. It means no more new, faster computers. So what happens to Intel then? I mean, what happens to our devices? Will we not have every 2 years a new nice iPhone? Well, that's something that's a huge challenge, really. So with electronics, there are certain limitations. The second global challenge that we are facing is data. Everything's going towards big data. And big data needs a lot of energy. Companies like Google and Facebook, they have their own data centers, and they put them typically either in northern locations, Alaska or so, if they can, read more recently, or they put them next to a river because they need so much power. They literally need a power plant to drive these data centers. So we have a lot of data, and the other thing is growing. The compound annual growth rate, is really, really fast. It's exponentially growing. And in the United States, currently there was a report from Stanford professor, we are already using 2.2% nationwide just to communicate. And look at its growth rate. So what happens in 10 years? In 10 years you use 110% or more than 100% of electricity for communication. Well, that's unrealistic. So we need to do something. So we fundamentally have a challenge that we need to address. And if you, for instance, if we communicate, GW communicates with KU, and we have some telecommunication, we use fiber optics to send information, and you can ask, so how many photons do we need to send a bit of information? It turns out we currently use about 100,000, and we kind of getting towards 10,000, but it's quite a lot. And what my group is looking into, for instance, is can we get to attojoule per bit? So can we get to 100, maybe 10 bits, 10 photons per bit? So we really want to get a quantum leap forward in this research. And on here is basically like this, also like a power problem. As we scale transistors, then these interconnects, power again goes up, and that's basically also very bad. So there's certain limitations again to electronics, and with photonics is great, but it's a really power issue as well. And of course we want to go faster and better. So the idea is we go from electronic circuits sort of to photonic or photonic electronic hybrid circuits. And this is some work from IBM here. This is, for instance, like an electro-optic modulator or a switch, which is sending data, and you get basically some kind of like data out. And this is something that we would like, that my group is also focusing in as a core. So within this background, photonics has been seen as one of the big solutions. Photonics and optics can go beyond those physical limits that we see often with electronics. And for instance, one of my colleagues here, Professor Erwin Zimzak, he has this like a new wave lab, and he is taking on some of these challenges. For instance, the idea would be also if we look into like sensing. And I think what I really should have done, I should have put, like, you remember like Star Trek? They have these tricorders, and they, like, go, like, they walk around, they kind of look, oh, I detect life signs somewhere, or so, like, it's like Star Trek shows. Basically, this is almost like what he's proposing, and the idea here is to combine nanomaterials, like these metal dots here, with new materials like graphene for conduction, and then with light as well. And then this will be a very, very effective sensor. And on the right, you essentially can see, for instance, an example of, let's say if you apply voltage to this graphene, we change the wavelength operation, we have two conditions like where it's dielectric or metal, and you can really effectively switch between these two regimes. And you can basically have a very, very good detector. And here's just some simulation work, and you can basically see the change of this resonance structure, and it's a very good sensor. The second thing that this group is looking into is essentially some sort of nanofabrication schemes which are very new, or not necessarily new, but very, very elegant, and they can be done basically on a tabletop system. For instance, here's a laser, and you have like a crystal here, and he basically has a sample at the other side, and then what you can do, you can send light in from one side and get sort of like higher harmonics, and therefore basically creates like a beam profile pattern that is above or below a certain threshold for your system. And then basically you can create some kind of like nanostructure pattern. And this is just like the first prototype here on this, still something to develop. But what you can see down here, if you track the reflectivity of such a system, you can really get a pretty nice cavity here, like a pretty good resonance, which can be used in shifted force for sensing applications. And the other part is, so let's say also like in terms of sensors, typically what you have maybe set up something like this. You have a big lamp, which is the housing of like big size, and you will do fiber, you have polarizers, you have an array. You have an entire big setup, which maybe is a meter long on your table. So going back to Star Trek, wouldn't it be nice to put everything like this into like a phone? And it turns out we actually can. And the keyword is photonics, and the second keyword is integration. So what we really want to do is we want to take these approaches, like making everything nanoscale, very small, and putting it as an integrated platform into systems like smartphones, for instance. I mean, like remember 10 years ago, you can buy a CC like a digital camera. It was very bright. You have a digital camera. It was a new thing, right? Or maybe 15 years ago or so. And now the the camera is somewhere here in some of these smartphones, and you use it every day. You take it for granted. Cameras of this size now. So can we do first the same thing with like sensors? Can we just put them in there? And then maybe sensors, as we heard before, may be very important to sense data, to gather data from your surrounding. And this is the way with photonics. We basically make the sensors. We are working towards these devices. Okay, moving on to another, this is actually our chair, Professor Mona Zagul from the Electrical and Computer Engineering Department. And she is looking into MEMS, and the MEMS is basically the same thing as micro and nanoscale. And the applications, in particular, she's also looking here into the biomedical sensing arena. And the idea would be here to design a particular sensing application where you can basically, like you and I, we don't have to go to the doctor, but we can just basically do this kind of treatment by ourselves, because we buy this kind of package, it's an all-integrated system, and we get some very nice reading from this. And what they're looking into, for instance, is tracing the alcohol content. When you have drunk something, right, you have a party, and then you drive the car afterwards, it's nothing dangerous, but it's also illegal, and then the police maybe stops you and then have you kind of breathe into like a system and then want to test your alcohol. So this is like, these kind of sensors could be made from this, as well as air quality, right? Anyone that's been to Beijing? So air quality is definitely a serious challenge for urbanization in cities. And basically they're developing systems here where they're essentially trying to sense these devices. So for instance, what she has here, she has like a nanowire sensor. So the idea is you have a single nanowire here, grown, and packaged into like a source and drain. So you can read like you can do true probe measurement. And as you change the concentration of, for instance, air, or in this case here on you're looking for methanol, you can really basically get a pretty sensitive reading on the current. So this is like a way to essentially make a sensor. And she's actually collaborating with the National Institute of Standards and Technology in NIST, which is just up in Gaithersburg, close to GW. And you can also do the same thing then for air, like for nitrogen, and you can basically see pretty reproducible examples of you basically turn on this system, and basically like you turn on this kind of like flow. I guess it's like air in this case, and it's nitrogen in this case, on and off, and it's very repeatable. So it's very like a very robust system. With this, I'd like to move on to my next colleague, Professor Samuel Lee. He's in microfluidics and also nanophotonics. He basically concentrates on, he wants to, for instance, do things like he wants to trap cells. So he has a microfluidic channel. So they have a very sophisticated kind of like, channel that they built, like a microchip or lab on a chip type system, and with a lot of valves and pumps and everything you need. And then here is a zoom in, for instance, into one region, and what you have here, they have a flow here of analyte, you maybe a blood sample or something like this, and then they can basically capture certain molecules in this area, and because they're captured here, they're localized, you know where to look for, and then there you can basically detect it and read it out. Another idea, and again, this again drills on integration, is, so let's say you have, for instance, like a typical optofluidic like system. It usually looks like this. You have optical table, you have lasers, and then here's your sample. You see somewhere here there's a pump, or something here's a pump into your sample. It's rather bulky. Can we just do the same thing on a small chip size? Very cheap for production, Intel, Samsung style, right? That's what we want to do. And the idea would be, yes, we can do that. And they fabricated such a system down here. And here's like a little coin as a comparison of this kind of system. And the other thing that's really nice about these systems is actually we can make them flexible. So they don't have to be stiff and hard and brittle. They can be very flexible. And maybe you can integrate them in clothes, like some kind of like clothes or gloves maybe, or something like this. Maybe wearable, and have also like a very low cost function. So this is work that's very actively done currently. And actually here in this inside here, you see all these different channels here are sort of like these microfluidic channels where you can release an analyte, for instance, for medical testing or for some other testing, and have a very good readout. So that's really like the power of flexible electronics that Professor Samuel Lee is focusing on. With this, I'd like to go to my group. Again, my group is working on optoelectronics and integrated photonics, and this is basically my homepage of my group here. It's still a bit in developing, and but please go to this. I think it's in my resume, which is in the end of the booklet that you have this page. The thing is, we want to concentrate on it. Basically, the pitch is the following. If you look at device architectures, so here's speed, how fast we can modulate something, and here's the device size. So the past is basically there. Everything was large and slow. And Intel came along and basically scaled, make things fast. Make things small, like towards nano size, gate length. But like your computer is still what, like 2 gigahertz maybe, 2.5, 3 at most, right? It's stuck there for like 10 years. And this is because of this interconnect data I mentioned earlier. Well, with photonics, it turns out, photonics is really great. Photonics has time scales on the order of nanoseconds. A lot of effects you have in nonlinear objects, which you can use for switching and data routing, are really fast, but photonics is governed by physics, the laws of physics, meaning the diffraction limit of light. It means you cannot make it smaller than half the wavelength. Doesn't work. So the idea would be to go to this quadrant, and the performance would be basically increased, and this is what I focus in. And we use nano optoelectronics, meaning semiconductors and devices in this kind of regime. So we try to integrate the best of both worlds, how we can be taught. And one vision is, again, that these computers and your smartphones in the future will run with light. There are little light paths inside your computer. And the trend, I can already tell you now, the trend, I have proved that we are going towards this direction. Because if we, like GW and KU, we communicate over email, essentially what happens, your email is converted into an optical signal, sent around a fiber, comes back and converted into a computer again. And so optics, we know optics is great, optics is good, but we use optics now not only for long-haul communication, but for local area communication, and in data centers from rack to rack. And then soon we go to on-card, and then you go basically intra-card, and then you go on-chip or intra-chip. And this is basically, and currently we are somewhere about here. So Google just like, Facebook and Intel currently made a partnership to design next data center generation, and they basically use now photonics to communicate between different servers. So the problem, however, is the input-output is bottleneck currently. The solution is basically going optical, and the advantages are higher bit rates. Your 10 gigabits per second rate, you really get them with photonics, or even actually much, much higher. Low loss, and it's actually scalable via nanophotonics. So we really want to do what Intel did for the last 40 years now with optics. This is actually our device setup that my group will be setting up very soon. Here we have tunable lasers, cameras, so to maybe just, in the network analyzers, optical spectrum analyzers, bit error testers. It's going to be a very powerful system for high-speed testing. In other words, I want to invite you, if you have a system, maybe an electro or optical system that you want to maybe basically test at high speed, come to me and we can work together. We do novel device detection, electro-optic measurements, and again for high speed. And this is one example of the work from my group. This is in scanning electron microscope, and it's maybe not clear what's going on, so let me highlight a few things. This is actually a photonic transistor, and basically like a transistor is a three-terminal device. Current comes from one side, goes out the other side, and you have a gate to control it. And we basically do the same thing. So we have light coming in, and here's our gate, and we have basically our data light coming out. And one thing I would like to focus here on is this part here. It's basically 3 lambda long. Lambda is a wavelength. That's super, super tiny. Typical devices of this is called an electro-optic modulator, are on the order of a centimeter. So we are essentially 1 micrometer or 3 micrometer long. That is 10,000 times smaller. And that's really the power of these new systems and these kind of metal optics and plasmonic systems. So we squeeze the optical mode to extremely tiny areas, enhance the field, and therefore get extremely strong interaction. So that's a very new approach. So how much better is it, you could ask? Well, let me show you. So we actually have these 3 matrices here: scalable, speed, and power. SSP. I always call it S square P. It's sort of by my personal metric, S square P. And we go basically like 10,000 times smaller in terms of speed. Remember, like these machines, gigahertz? These switches, these optical switches, they can go up to terahertz now. And this is something we would like to explore and measure, and this would be really a big, big breakthrough. So this is basically for a single data channel. If we then use WDM, waveform division multiplexing, we can go to not only to, we have 1 terabit per second for 1 channel, and let's say if you use 100 channel, we basically have like 0.1 or basically 100 terabits per second lines. And that's just like for a single fiber. And that we can basically put into the computer and into your smartphone. All right, so what's in the pipeline? Meaning future research. And this is something I would like to invite you as well. And I think Professor Lee's lab that we visited this morning was very interesting. He's basically growing these graphene layers. And here's, for instance, like a proposal of something that I'm interested in also looking into. Is essentially like a solar cell, like a new type of solar cell. And the idea would be we replace the top contact, which currently is aluminum, which reflects a lot of light, with what's called a transparent conductive oxide, or transparent conductive material. So we use graphene because it's very highly conductive, and yet it's monolayer thin, so all the sunlight can go through and actually reach the solar cell and does not get reflected. So it's very nice. And then we can maybe use these PIN junction nanowires, array, which have to be shown to have a really high efficiency in terms of absorbing sunlight. And this could be a very brand new system. I've not seen anyone working on this. So if you grow nanowires or graphene, please talk to me, or let's get after this together and we talk about this. And here's just like one system that I've done. Like a little bit while back, we published in Nature. Essentially, it's a this plasmonic laser, like a tiny laser. And look, the mode is so small; it's just about 5 nanometer. That we can maybe interface this with some kind of like microfluidic system, and we can actually detect single molecules, like for instance the DNA. This could be very interesting for DNA sequencing. Well, with this, I'm at my last slide, and again, you have heard about this morning here about our science and engineering hall, and we will have a clean room in there, which will enable all or a lot of this research that I showed today here. And again, a clean room is really the place to do nanoscience. We do, wafer fabrication, but also like like small applications or small scale. It's a state-of-the-art system, so of course something like this is way obsolete, so we want to do state-of-the-art research, and this is the place that enables this, and it's really a multi-R&D facility, so it's not only good for electronics, for photonics, it's also good for bio and all subsequent immersion fields. So with this, I'm happy to take any questions. Thank you.
Next speaker for this session is Professor Chun Lee. He is from Electrical Engineering Department is going to talk about carbon nanotubes for various applications. Okay, let's welcome Professor Lee.
Thank you, Chairman. Good afternoon, everyone. Welcome to Korea University from George-Washington University. My name is Jin Lee. Today, I will briefly introduce the nanotechnology research work at Korea University. Research topic on nanotechnologies mainly consists synthesis and characterization of carbon nanotube, graphene, nanowires, and decarbonized materials. Second topic is field emission from nanostructured materials and their various applications. And the third topic is flexible, transparent, simple and transistor devices using carbon nanotube, graphene, and decarbonized materials. And the fourth topic is flexible field effect transistors using silicon and gallium arsenide nanowires. Especially this kind of devices was made on the plastic substrates. And fifth topic is superconductor, supercapacitor, and energy harvest applications using carbon nanotube films and nanowires. The last topic is synthesis and characterization of silver nanostructured materials. There are many research groups on nanotechnology at our universities, so I cannot introduce all the laboratories in here, but I will briefly introduce our research interest and activities shortly. As you know, the many professors, 5 professors from School of Electrical Engineering and 4 professors from Department of Material Science and Engineering, and 3 professors from Chemical and Biological Engineering, and 3 professors from Mechanical Engineering. Besides these professors, other professors also has much interest on nano technology and nano technology convergence areas. Carbon nanotubes, especially nanocarbon materials, is very interesting and attractive due to their various diverse excellent properties. You can see here zero-dimensional fluorine materials and one-dimensional carbon nanotubes and two-dimensional graphene. Due to their unique and excellent properties, so we can consider many kinds of interesting applications, nanoscale transistor, flexible devices, and field emission display, the lamp, backstage source, the composite material, and energy applications. Recently, we are starting on the flexible, transparent, simple transistors using decarbonized materials. We are fabricating TFT transistors on the silicon substrate. Normally, it indicates decade. However, our final goal is to flexible and transparent simple transistors on plastic materials. Here you can see many kinds of nanostructured materials achieved by our university groups. Carbon nanotubes, many kinds of carbon nanotubes and graphenes, and nanowire materials. Among the interesting application topics, we are focusing on the field emission properties and their applications, because carbon nanotubes are very promising and interesting nanomaterials which can present very excellent field emission properties. You can see here some field emission based ramp. And also the other interesting topic is flexible electronics. So we can produce the flexible, transparent, simple transistors. using CNT film, graphene, or decalculated materials. Okay, especially, I'd like to introduce field emission properties and their applications. You can see here real field emission display made by Samsung Electronics. And this is the flat panel ramp made by carbon nanotube emitters. And also this is signage board and ramp. And recently, we are very interested on the point type field emitters, especially this kind of technology will be used to the future generation carbon nanotube-based X-ray source. So if we use this kind of technology for X-ray source, we can reduce the size and efficiency. We can see here the coin scale X-ray source and the battery scale X-ray source. This is really high performance, high power carbon nanotube-based X-ray source. So we started the field emission from 15 years ago. And you can see here microwave devices made by carbon nanotubes, and the study field emission properties, many kinds of carbon nanotube materials, and also by attaching some nanomaterials, namely the hybrid nanostructures, we can increase the field emission properties. And also we studied the high performance field emission ramp or emission source according to the process conditions. And recently, we made the very high performance carbon nanotube-based field emitters using our unique field emission carbon nanotube field emitters. So eventually, we achieved the very high emission current, about 500 milliampere per square centimeters. The result was 100 times higher than the conventional carbon nanotube emitters. And also, interestingly, we studied the flexible carbon nanotube-based flexible emitters. So we embedded the carbon nanotube emitters on the plastic substrate, and we can operate the stable field emission performance and confirm the stability of these flexible emitters from the bendable conditions. And we tried to get the high performance point emitter using carbon nanotubes. If we can reduce the emission size from the millimeter scale to several tens nanometer scale, we can enlarge the many kinds of applications for the future X-ray source or e-beam source. So anyway, from our point emitter, we can get extremely high emission current with very small emissions path. And recently, we tried carbon nanotube film point emitters from this kind of carbon nanotube emitters. We can get 15 milliampere. This is the real extraction current, not square centimeters. We also studied the field emission properties from graphene materials. Graphene also indicates relatively high emission current and good emission stabilities. However, compared with the carbon nanotubes, their emission performance a bit lower, stability is a little low. However, we can use graphene for some kind of emission applications. And we also studied the field emission properties from zinc oxide nanowires. According to the shape, we can get high emission current. When we compare the emission performance from the many kinds of nanomaterials, still carbon nanotube is number one, and the graphene is acceptable. And point emitter also, we can see the carbon nanotube is very powerful. high emission current, low Thorne fields. So we suggest it is not yet realized technology. However, the future generation field emission application, such as vacuum nanotransistor or X-ray source or even source, that we can use the carbon nanotube or graphene as a more effective and powerful field emitter source. Let's move to the topic, flexible electronics. We are managing national project, world-class university research project, flexible nanosystem research groups. So professors of electrical engineering and 2 foreign professors joined to these groups. And our goal is to realize the flexible transparent electronic system on the plastic substrate. So we studied many kinds of carbon nanofilm and evaluate their electrical properties. And we studied the TFT transistors using carbon nanofilm as a channel, and also evaluate the TFT performance devices. And recently, we are developing flexible transparent simple transistors using carbon nanofilm channels. And also, we are studying the synthesis of graphene. The one is the mechanical exploration, the other is chemical exploration. So recently, we are focusing on the CVD-grown graphene materials. One is the conventional summer CVD, the other is plasma assist CVD techniques. According to the chemical doping technology, we can get the bending of open graphene materials and made the TFT and checking the on-off performances. Still, the on-off ratio is not so high level. However, we can find some clue to open the band gap from the graphene and from the some doping technologies. So we are still working on these technologies. And recently we are studying the catalyst-free graphene dose. One more interesting topic on the flexible electronics. So we are studying the carbonate materials. So we are make the molybdenum sulfide bright and transfer this sheet on the silicon substrate and measure transistor performances. The on-off ratio was 10:7 because the carbonate materials have very wide band gaps, very stable. So we consider this material will be very interesting and powerful application for future flexible electronics. Professor Kutegin studied make the carbonate films using the mechanical and chemical approaches. And one research group studied the logic gate using gallium arsenide nanowires. His group studied and developed this logic gate on plastic substrate. And also, his group fabricated the memory devices using silicon nanowire on the plastic substrate. And one more group, the other group reported and studied energy applications, flexible electrochemical supercapacitors made by carbon nanofilms. And also, his group has studied the energy harvest application using these novel nanowire materials. And other group studied continuously have studied memory devices using nanocrystal materials. And the other group studied the silver nanomaterials, especially a polymer library using silver nanoplate synthesis. And this is the hierarchical structures made by silver nanostructures. So many groups have their interesting and unique research types, sometimes duplicated, sometimes separated. So we have some collaboration according to their research project or interests. So I'd like to discuss our future research items or topics from the detailed discussions. Thank you very much.
Thank you, Professor Lee.